Syzygy, episode 28. All exoplanets are exciting. Yes, welcome back for another edition of the Syzygy podcast, for the first one for 2019. There's been a bit of a break. We had a bit of a break over the Christmas New Year period. Some of you who listened to the last episode might remember that I was sitting alone in the dark and cold of Emily's office because Emily was overseas down in New Zealand, just gallivanting around, climbing mountains and enjoying the warmth. But she's back. She's back in the Northern Hemisphere winter. Emily, welcome back.
Thank you.
You're very welcome.
Remember that I was also sitting alone in the dark during that time.
Well, yeah, but I mean that was voluntary. I didn't really have a choice. I could have escaped the winter, but I couldn't really. So you were down in New Zealand. How'd it go?
It was brilliant trip. Unfortunately, the weather was not so fabulous for my observing, and it didn't actually get any better since we recorded. But
so it conspired against you a bit. But did you manage to get some decent observing done?
We managed to work on another project as well, getting another instrument commissioned onto the telescope, and that was very successful. So some good things came out of it.
Cool. And at the very least, you got to hang around in a very beautiful part of the world. I saw a lot of your photographs on Facebook. Thank you very much.
Yes,
of, crystal blue glacial lakes and mountain tops and
white sandy beaches.
Yeah. You're looking a bit tanned, actually. Have to say, you've got some colour that isn't sort of pasty white northern winter whiteness.
Well, trust me, it will not last here.
yeah, it'll fade pretty quickly. Well, yes, indeed. Welcome back for 2019. It's going to be a big year in astronomy. And in fact, we've already kicked off in a big way. Just last week, there was, now let me get this right, it was a super wolf blood moon, which just sent the newspapers and the TV networks absolutely mad. What does it mean, Emily? Super wolf blood moon?
So I'm really thinking I'm becoming an eclipse guru now.
I think you probably are. You're the go-to person for eclipses on Sky News, at least. Other news networks are available. Tell us, what's a super wolf blood wolf moon?
How many
moon?
Yeah. Well, if we break that all down and to look at all the individual words, they each individually mean something.
Okay, good.
So, well, some things more than others.
I saw someone on Twitter the other day saying, whatever happened to the days when just an eclipse was enough to get up for? Now it has to be a super blood wolfman thing. Just, no one's getting out of bed for anything less than a 4-word description of this eclipse. Whatever happened to just eclipses are cool? I don't know.
I'm still definitely on the page of eclipses are cool.
Yeah, but you're an astronomer nerd. I mean, you're supposed to be. That's in your job description.
Yeah, getting up at 3:30 in the morning is just part of it.
Yeah. Anyway, take us through it.
So super means that the moon was actually usually a bit bigger than it normally is. So the moon's orbit is not quite a circle. It comes a bit closer to the Earth at some points in its orbit. It's only about 7% bigger, something like that. So it's not actually easy to tell that it's bigger.
Right. So if you went out on any given night and looked up at the moon, you wouldn't necessarily think, gee, that moon looks big tonight. That's a super moon.
No, although you often do go out and look when you see a full moon. It looks really huge in the sky, especially if it's very low down. And we'll talk about that another time, I think, because it's a really interesting optical illusion. But because the moon doesn't really...
No, it's not.
Size.
It's not that big.
No.
If you take it into perspective, it's actually quite small in the sky. But anyway, let's save that for another time.
So supermoon, I mean, what it does have an effect on is, of course, things like tides, because you get more gravitational force from the moon when it's closer. It pulls up the tides a bit more.
Right.
So king tides are up to do with supermoons as well. Okay, so we have super. What was the next one?
Super wolf blood moon? Super blood wolf. Let's choose wolf,
okay.
Right? Wolf.
Wolf has absolutely no meaning whatsoever.
Really?
So it's a cultural thing. It just means it's a moon in January, a full moon in January.
Oh, okay. So a wolf moon, a full moon in January is a wolf moon.
And I've never actually heard that before.
Okay.
So I think that might fall into the realms of astrology.
Right.
Perhaps.
Well, we'll look that up. I'll go and see if I can find a reference to that and put it in the show notes. It's got to be on Wikipedia, surely. We'll find it. Okay, so it's a wolf moon.
Not quite as interesting, that one.
Big deal. Sounds cool. Okay. Blood moon.
Blood moon is a lunar eclipse.
Right.
And it's a total lunar eclipse.
And it's called a blood moon because it goes red.
Yeah.
And it goes red because...
Because the blue light, so the sun is illuminating the surface of the moon. It makes it the glow and the white colour because it's getting all of the colours from the spectrum. When the light passes through the atmosphere of the Earth, then only the blue light is scattered around and absorbed, so only the red light is able to pass through onto the surface of the moon.
Right, so when the moon's in the Earth's shadow, it doesn't go completely dark because some of that light's getting sort of bent around through the Earth's atmosphere. But the light that gets bent around and not scattered as much as the red light. So that's the same reason why sunsets and sunrises tend to be on the red side. Is because the blue light's all getting scattered. That's why the sky's blue. And the red stuff is what's left over. And so that's what you see at sunrise and sunset and during lunar eclipses, blood moons.
Yeah. If we didn't have an atmosphere, interestingly, the moon would just vanish entirely. We wouldn't be able to see it at all.
Which would also be cool, but this I think is more interesting. Okay, so that's the blood and then moon because it's the moon. So super wolf doesn't mean much. Blood because it's red. Moon because it's the moon. Well done. And you did a little bit of TV on this last week. You are becoming the go-to person. That was a bit of fun.
It was really fun, actually. Yeah. So just got to talk about that. Talk about why the eclipse happens and so on, and then get the curveball question kind of at the end of why do people go a bit crazy in the full moon? But we don't have a real scientific answer for that, but. At least
that's got to be psychological. It's a full moon. It's an excuse. Now I get to act up and go a bit nuts because it's a full moon, and no court in the land would convict me. But the other really cool thing about this eclipse, taking aside the fact that no one gets out of bed for anything less than a super blood wolf moon these days, people who were taking photos and videos of this thing last week actually captured something really, really interesting, was that there was a meteorite impact on the moon during the eclipse while people were taking video of it. They captured this.
Yeah, and fascinatingly, there were two, actually.
Two within the eclipse, which is really cool because this is the first time that anyone's ever actually caught this on video. Like, things hit the moon all the time. That's why the moon's covered in craters. Yeah, I mean, things hit the Earth all the time, but most of them burn up in the atmosphere. Moon doesn't have any atmosphere, or none to speak of. But so things are bashing into it all the time, but not typically when people are watching it really, really closely because there's an eclipse going on.
No, and the moon's normally way too bright for you to be able to take those kind of images. So when it becomes much, much dimmer during an eclipse, the contrast between the brightness of a meteorite hitting the surface of the moon is really blown up, and you can capture that with even some, fairly amateur equipment, which is amazing.
There's plenty of videos out there. I'll put some links in the show notes as usual, but when I first saw the link to one of these videos and the headline was like, wow, asteroid or meteor impacts with moon during eclipse, I've got to go and see this. And you're watching it and there's this full red moon and here it comes. And they put a little circle on the moon. It's like, watch this spot. And then it just goes, and this tiny little white flash. And then they zoom in on it and put the circle around again. Watch this spot. And it's still 1 pixel of brightness. And you realize, of course, the moon's really big, isn't it? And, I was expecting this huge explosion. Wow, look at that. And it was just... And so initially I was really quite underwhelmed. And then my brain kicked in and went, no, think about it. You are watching the impact of a meteorite on the moon on video. That's real. Wow, that's so cool.
And during a lunar eclipse, which just makes it super, super cool.
Very cool. So, this got all over Twitter and there's lots of videos on YouTube and so on. You should check them out. And I have it on good authority that the moon people at NASA and the ESA and so on are all over this. And they're all going, well, we could pinpoint where these things are and maybe send one of our probes that's in orbit around the moon to go and just see if they can see these brand new craters that have been formed by these two impacts. So that's kind of cool.
Yeah, it's so exciting. The solar system in action.
Yeah. The only trouble with this is that this is just going to make it even harder, right? That now in the future when we say there's going to be an eclipse, people are going to go, yeah, but is there going to be an explosion too? Are we going to, is it going to be worth my while? If I'm going to get up at 3 a.m, you got to show me aliens at least,
Well, I do have some bad news for you on that front.
Yeah.
If you're in the UK, then we're not going to see another total eclipse of the moon like this until 2029.
Oh, that's a long way.
It's a long way.
That's like another 10 years.
Yeah.
That's hardly fair.
No. So, well, option one, be somewhere else.
Well, true, actually. Yeah, good point. Where should we go then?
Well, there's going to be lots of lunar eclipses. There's usually a couple every year, or at least one total every year. So you just sort of meander around the globe following the eclipses.
I think we should have a syzygy field trip. I think that'd be good. Yeah, if anyone wants to reach out to us and sponsor that, we would love to take your call. So just get in touch.
And we should mention that there are going to be 2 solar eclipses in the next 2 years. So even like more dramatic and more astounding.
Are we going to see those here?
No.
In the UK?
No.
So where would you have to be
So
to see
both
that?
of those, the tracks pass through South America.
Ah.
So with a lunar eclipse, basically nearly half the world can see a lunar eclipse at any one time because the Earth's shadow is really big.
Compared to the moon, yeah.
Yeah. So, but the moon's shadow is really, really tiny. So it only falls on a very, very small part of the Earth.
Yeah, there's videos from the last big solar eclipse taken from... Would it have been from the International Space Station or from some kind of satellite showing the shadow going across the face of the Earth? And you look at it and you think, wow, it actually is really quite small, isn't it?
Yeah.
Yeah, that kind of makes sense, I guess.
Yeah, so you've really got to go to the exact location for a solar eclipse.
Well, I mean, I could see a mountaintop in Chile. I think that'd be fun.
I think so.
I think we should go. All right, look, reach out to us if you've got the cash to send Emily and me. Look, we'd settle for business class going to South America for that eclipse at some time within the next couple of years. Get in touch. We'd love to hear from you. So, okay, moving on to the actual news of this particular episode. Long-term listeners of this show know that we are big fans of a particular small but incredibly valuable satellite known as TESS, the Transiting Exoplanet Survey Satellite.
Well done, you got it right.
I did. I didn't even have to think about it. The gears in my brain were going really, really quick over that one. And that launched, when did it launch? Last year?
April last year.
April last year, very early on in the annals of this particular podcast. And we have a great interest in the satellite, not only because it's looking for exoplanets, which is cool, and the baton's been passed to it from the Kepler mission to TESS as the main exoplanet hunter, but also because sitting opposite me here in the Syzygy studios, Emily's got a real interest in this because it actually overlaps quite strongly with your research area, which is variable stars.
Yeah.
So the first bunch of data, the first bunch of scientific data has been released from TESS in the last little while. Emily, do you want to talk to us a bit about some of the excitement that's come out of that? Because it's pretty cool.
It is so cool. And so we got the first data drop, if you like.
First data drop. Here we go. Here's the big box full of printouts from the dot matrix printer.
So NASA uploaded it all to the interwebs, and we got that on the 6th of December. So it's actually public data. Anyone can go and have a look at that. It's through a database service called MAST, which is actually where you can get lots of really interesting space telescope data if you're so inclined.
Yeah, if you're really into this sort of thing, then you can go and check out the
Hubble
actual
data,
raw data.
Kepler data, it's all there.
People have been doing amazing stuff, actually, just parenthetically, tangentially. People have been doing amazing stuff with the, what was the mission that went to Jupiter over the last while and took some amazing, it was a Juno mission. And people have taken some of the images from Juno, so raw images, and turned them in the most extraordinary pictures. And that's just, Joe and Josephine average around the world going, let me get my hands on that data and play with it. It's great. Anyway, this is test data. You can get your hands on it. What could they find?
There's lots and lots of really interesting things. And NASA obviously are putting out lots of releases saying, oh, look, we found this thing. We need to go and look at it because it looks really interesting, but we don't really know if it's a planet. We don't need to have some confirmation of that. So what they put out when they look at the test data for the very first time, or even as it's being collected, is you get something called targets of interest, TOIs. And there's something like 200, nearly 300 targets of interest already being put out. And some of those were in the data release that came out in December. And some of them will come out as we see more and more data coming through. So the way that TESS works is it looks at a chunk of sky for about 27 days, so just shy of a month. And each of those chunks of sky are called sectors.
Right. How big is a sector?
Nearly a 1/12 of a hemisphere. So if you imagine that TESS is going to look at the entire southern hemisphere, it looks sort of about 1/12 at a time.
Right. So that's actually quite a big chunk of sky.
It's a huge chunk of sky.
In comparison to, for example, the Kepler field of view, which was really quite small.
Really, yeah. So Kepler fits within 1/4 of one sector.
Okay.
So it's just a huge, huge amount. So it's about 400 times more sky, I think, that TESS is going to look at than what Kepler.
Right. And so each one of these chunks, it's looking at for 27 days, on the go, non-stop.
Yeah. And, there's a download in the middle and then there's a download at the end.
Right.
So we get 2 bits.
So that's a lot of data.
It's a lot of there's a lot of stars in here.
Wow. Yeah. That's more than a floppy disk.
Yeah. Well, it's a few gigs at least. Poor old Tess. So each sector, they started science observations on the 25th of July. And so
before that, it was all sort of aligning cameras and
commissioning. And there were some interesting things that we found in commissioning, which we'll come back to. But then we started kind of science. This is full on. This is go. And it was on the 25th of July, so it ran for about 27 days after that, so mostly in August. And that was Sector 1. And then we had Sector 2 similarly running for about 27 days in September. And those were the 2 sectors that were released in December. So they're doing a pretty good job because it's not really a case of satellite download data, push go onto the interwebs.
Yeah. It's not like TESS has got its own web page and it's just dumping it all on there itself.
No.
Here you go, have at it. I'm assuming that there's a few people who kind of trawl through that data first to just make sure that things are looking okay and getting it into the right kind of format and that sort of thing?
Yeah, there are huge amounts of work that go on behind the scenes, taking that data and turning it into products that astronomers can use and that anyone can use. So, for example, you're taking an image, basically, of the sky. You've got one camera has 4 CCDs that are taking the images, and so you need to therefore go from an image to what we call a light curve, which means you've got to find one star in your image and look at the brightness of that star changing over time. But that star can move in your image, so you've got to watch it moving around. Shouldn't move too much, but it can move.
Yeah, if it's moving too much, it's probably not a star. I think, I know enough to know that.
But this is just the satellite stability as well. You've got to make sure that the satellite doesn't wobble too much, so that the stars and that particular star can take up many pixels in a particular image. So you've got to extract all those pixels, combine them all in a really sensible way, and put together this light curve, which is brightness over time for these individual targets.
Yeah, because it's pointing out that astronomy these days is not about, hey, look at the pretty picture at all. It's about what's the data in that picture, what's changing over time, what are things doing, and that's not images, that's graphs, that's data, that's time series, that sort of thing.
Yeah, so it's a lot of processing because then you've got to repeat that process for thousands of stars in every one of the image. And they're not done by hand, unfortunately, otherwise some poor person would get very frustrated. But the process, the code, the computers that are doing this need to be well trained, and we need to be very, very confident that they're doing the right thing with that data.
So all of that work behind the scenes is dragging out of all of these images, all of this data, targets of interest. That it's basically saying you can ignore all this other stuff. Here are the things to focus on, because there's huge amounts of data. There are enormous number of things you could look at. These are the ones you should focus your time on. Is that right?
Well, actually, they pull out more than just the targets of interest. So they pull out all the stars that were pre-identified before the mission before TESS even launched. These are the stars that we're going to extract. We're going to get data from them every 2 minutes, and that's going to help us build these really precise light curves. And there are hundreds of thousands of stars that fall into that category. And then you get the full frame images. So if your star didn't happen to be one of the special stars that was selected to have this extraction done every 2 minutes, then you can see the whole image that was taken of the sky every half an hour. So you can still extract.
Right. So you can do it yourself. You can roll your own, as it were, just because someone else has decided that yours isn't one of the targets of interest. You can say, well, it is to me.
Yeah,
so
exactly.
I'm going to go and have a look at it.
But you won't get the data as often because we can't download all these images every 2 minutes. We have to only download a smaller number of stars every 2 minutes.
That makes sense. Okay, so out of this first wodge of data, what's interesting? What have we found?
So, the TESS science team and the TESS Exoplanet science team have announced 3 brand new confirmed exoplanets. So that's super exciting.
That's cool. Just out of the very first bunch.
Yeah. And there's some very, very interesting characteristics. I think we should talk about each of those.
Okay.
But we're also looking at other things, of course. In fact, this is a fun fact. What do you think was the very first announcement that Tess made about something that it had seen that was quite interesting.
Oh, I don't know. I mean, if I was in charge of Tess PR, then I would be going, okay, well, we want to make a bit of a splash. So, I don't know, we've seen something that's a bit Earth-like, or we've seen some kind of funky exoplanet around another star, and here's why it's so cool. That would be my guess.
So the first Tess announcement wasn't an exoplanet.
Okay.
And it wasn't a variable star. It wasn't a supernova.
So it wasn't any of the things that Tess is actually designed to do.
It was a comet.
Of course it was, because why not? A comet?
Yeah, so this was a comet. We actually did know. Tess didn't discover it. We did know it was there. So we looked for it, basically, in the Tess data. And this was Tess during commissioning. In fact, it was just before it started its science mission on the 25th of July. And so they had a look and so to see what was going on and how the image would look if we looked at a comet with Tess.
Give it a shot. I mean, try it out. See how it goes.
Yeah, and we'll put a link to the result, because the video that they made of stacking kind of the images that they took is just fascinating.
Yeah,
you sent
me this video in the lead up to us recording the show this morning, and it is quite extraordinary. I mean, there's this series of images. You can see the comet going across the sky, but there's, at first glance, like, okay, yep, that's the comet. And then you look into it more deeply, and there's just so much in this series of images. You can see the tail of the comet sweeping around, changing direction as it moves through, around through the solar wind, and the solar wind sort of pushing the tail off behind it. So you can see that changing direction. You can see, in the sequence of images, you can see asteroids just moving across the background of stars. These tiny little light dots that are shifting across. You can see that. Just so much stuff. There's a couple of variable stars in there that you can see.
So the stars themselves don't move. So you can see it really highlights the motion of the comet or the asteroids that you're seeing. Some of the stars, you can really see the brightness changing over the course of the images.
There's just so much going on in these images. Exciting. And that was this isn't even the science run. This isn't even the science. This is just the tuning up data. Let's have a look at a comet and see whether that works. And there's so much in that already.
And it gives you an appreciation of how much data processing needs to happen as well, because you sort of see some of the stars go black for a little bit. That's just the extraction and the processing that we have to do to the data to get all the really high precision signal that we need out of it. So,
very, very cool. Go and have a look at it. We've got the link in the show notes. You really should check that one out. So 3 exoplanets.
Yeah.
Talk us through it. What have we found?
So these were released, announcements were released for these over not just in this month. We saw the first 2 were announced at the end of last year, but I thought it worth talking about the first 3 altogether because they're kind of nice.
That's a milestone.
So the first one was in September last year, and it was found actually in a really interesting system. So this is an exoplanet that was found around a star that we already knew had an exoplanet going around it.
Right, okay.
But this is another exoplanet. So we knew about one already in the system, and we added a new one.
Right. And so the one that we'd already found, I'm assuming, was probably the bigger of the 2?
It was, but it's not quite the sort of system that you might expect.
Okay.
So the star's called Pi Mensae, and we knew that it had this super Jupiter-sized planet going around it. And this was detected using radial velocity techniques. So it's huge exoplanet, and it's got a period of something like 6 years.
Right. Okay.
And it's it's on a pretty long orbit, which means it's reasonably far away from its host star. Now, the planet that they found is almost the polar opposite of the one that was already there.
So small, and close.
It's a super Earth size, so maybe twice the size of Earth, something like that. And it's got a period of only 6 days.
6 days?
6 days, which means it's whipping really around the star. Right?
Wow.
Hurtling around it.
Hang on, just for reference, Mercury's orbit is
88 days.
88 days. So it's really close.
Really, really close.
Wow. But it's twice the size of Earth.
Yeah.
Wow.
Amazing. And so really interesting system. And we got to look at it and start to think, well, how is this system put together?
What's going on?
Yeah. The star itself is not too dissimilar from our sun. It's only a little bit younger than our own sun. And but what's really crazy is that the big planet, the super Jupiter, if you like, has a really eccentric orbit. And that means it's not going around in a nice, tidy, organised circle like most of our planets in the solar system.
It's on a big ellipse.
It's on a big ellipse, almost like a comet. It's the eccentricity is about 0.6, which is huge.
That is big. So that means that sometimes it's much closer And sometimes it's much further away than the average. It's on this big stretched out ellipse.
Crazy planet. And actually it moves into the habitable zone of the star from time to time. So it's really, really interesting on its own, and it's an interesting system. But then when you think about the orbital dynamics, we think that would mean that if you've got this big planet coming into quite close to the host star, how on earth do you have little planets sitting in there? The gravity from this super Jupiter should totally disrupt any sort of interior planets and basically either kick them into the star, they'll explode and burn up, or kick them out into the into the interstellar medium.
Fling them
and just
out into the
outer
void.
Space, yeah.
So, that's really weird.
How do you have a stable orbit with you've got that big giant coming in to disturb you?
That's a really good question. I'm assuming we don't have an answer to that yet.
No, we don't.
Right.
But that's what makes it so exciting and so interesting.
Particularly as, this is the first one. How cool is that? If the first planet had to be discovered in the test data had been, yep, it's a planet, just as we thought. But instead it's a planet, but hang on, everyone just pause for a second. Just look at this system. This is nuts. Then that bodes well for the future, right? There is much stuff to work on.
And what's so exciting is this is a bright star. In fact, you can see it with the naked eye if you go into a dark place, and obviously in the southern hemisphere, that's where Tess has been working.
And you know where to look.
Yep. And it's not very far away. It's only about 60 light years away. Which sounds a long, long way away.
It is a long way. I'm just doing the mental calculations and I've got nothing. Give me some sense of how far away is that? What's the closest star to us other than the sun?
So that's about 3 light years away.
Right. Okay. So it's within sort of the closer bunch of stars to us. It's not too far.
It's
away.
not very far.
Yeah, okay.
And that means we can get really good quality data on it. We can follow up this observation for a long period of time and just really drill down and get some more data out of it.
Cool. So that's the first one. What was number 2? Did number 2 sort of, I'm just a planet. I'm nothing special.
There's no such thing as a boring exoplanet is something I'm thinking that's probably true.
Good. Okay, so number 2.
Number two is around the object is called LHS 3844.
Beautiful name.
Yep, the planet's B, because we stick a B on the end of it. That's so the star's name is.
Remembering because we don't do A's.
No.
For no apparent reason.
I haven't worked out why we don't do A's.
Well done, astronomy. Okay, so planet B. Yeah, the first one.
Yep. So this was discovered on the 20th of September. So again,
very early on.
Early on in the mission. Now, if you thought that the other planet was kind of a bit quick, going around in 6 days, this one's going to blow your mind.
Go on.
It goes around in 11 hours.
What? That's just how? Okay, so how big's the star?
It's actually quite a little star.
Right.
So it's what we call an M dwarf, which means it's quite small, quite cool, probably on the verge of even being allowed to be a star.
Barely a star at all.
Yeah.
But bright enough to see something going around it. So, it's a star.
It is, it is fusing. I mean, we can't be too mean to it.
11 hours?
11 hours.
How? That's next door. You could reach out and touch that.
Yeah.
That's crazy.
If you lived on this exoplanet, a whole year would take you less than, a day here on Earth.
That's a roller coaster ride around that star.
Imagine
that's
how
nuts.
old you would be.
Yeah, exactly. Well, that's not quite what I was thinking. I was thinking more like you've just been burnt to death. But sure.
Well,
yeah.
I'm just thinking, wake up every morning, have a piece of birthday cake.
Well, don't even have to wait for the morning.
Before you go to bed at night, have another piece of birthday cake.
One for dinner, one for breakfast. Just constant birthday party. I like it. But wow.
Yeah, but obviously this is really, really close to its host star. So it's not the most fantastic place to live.
No, we're not going to be looking at this one for extraterrestrial life, I don't think.
Your candles will self-ignite.
That's right. Your candles and everything else around you will be on fire constantly.
Yeah, so it's probably a lava world. They're calling it a hot Earth.
Well, that's an understatement. Well done.
Yeah. It's not the most, but it's interesting. It's interesting that you can get. This is one of the closest exoplanets orbiting its host star that we've ever found. So super, super interesting.
So, okay, the first 2 have been really kind of interesting. I'm holding my breath for the third one. It's either going to be really dull or this is a planet that's made out of Stilton cheese. And we know it because, tell me about planet 3.
Well, it's going to be the second case. Not so much about the cheese, but the fact that it's going to be really interesting.
Yeah, okay.
So this is the third one. It was announced at the American Astronomical Society meeting on the 7th of Jan. So super news, and that's why I thought this is a great time to talk about these early discoveries.
Yep.
So it's called HD 21749b.
B.
Right. And it is one of the coolest planets that we've found around a star, which is the brightness that this host star
Now,
is.
when you say coolest, you're not talking temperature, you're talking awesomeness here.
Well, I'm talking both, really.
Oh, okay.
Yeah. So it's a mini Neptune is one of the ways we can describe this. So similar to Uranus or Neptune in our solar system, it's only 3 times the size of Earth, but it's much, much more massive.
Right.
So we think it's one of these kind of icy gas giants that we have. What's really interesting about it is that it doesn't seem to be quite like Uranus and Neptune in our solar system, in that it seems to be much, much denser. So our ones are big, fluffy puffballs, basically.
Yeah. I mean, they're gas giants.
Yeah.
They're not on the same scale as Jupiter and Saturn, but they're big.
Yeah.
And they're gaseous. They're not solid. They're not made of rock.
Yeah, so this one's not solid either, but it's kind of somewhere in between those things. So maybe kind of quite a dense gas, or
Like
maybe more like water.
I'm thinking a slushy.
Yeah.
Like maybe not
good-
completely icy like a slushy, but it's a slushy planet. You can have that one, Astronomy World. You can have that for free.
Cool. So it's on an orbit of 36 days.
Okay, that's pretty quick.
It's pretty quick. Now, you'll notice actually...
Hang on. Thinking this one through. This is cold. It's a cold planet. Yeah?
Yeah.
36 days, which means it's really close.
Yeah. So what does that
How's
tell you
that
about
work?
the star?
Star must be really cool.
Star is really, really cool. So it's a K dwarf. So it's a bit warmer than the one we just mentioned, but it is a small, cool star. So the star itself has a surface temperature of only 4,500 degrees Kelvin. It's kind of the same.
Only. Whereas our sun has a surface temperature of, what, about
6,000?
6K?
Yes,
6,000?
slightly more.
Yeah.
So that makes it a lot cooler, which means that the heat output, the light output is, well, the light output's the most important. That's much, much less.
Right. So you can have a slushy planet with an orbit of 36 days, which is pretty quick, but it's still not really, really super stupidly hot because the star itself is quite cool.
So we think the equilibrium temperature might be around 150 degrees Celsius, which is hot.
That's hot. But there are hotter places.
Yeah, but it's cool for one of these types of planets. If that makes
gotcha.
sense. Yeah,
Gotcha.
Yeah, and so very, very exciting. Something we hadn't really seen before, and it's great to have these big gaseous planets that are cooler because we know a reasonable amount about hot Jupiters, say.
Right.
So these are the big planets, big and gassy, that are very close to their host star, and some of them are thousands of degrees. And so we've been able to study those quite a bit because we know of quite a few examples. And these are the ones that we want to try and work out what their atmospheric composition is. And we have some that we do have some really good data on that. So this is an example of one of those cooler example.
The slushy Neptunes.
Yeah, end of that sort of spectrum. And so for the first time we can start to look at, well, what are they composed of? Is it different or is it the same as the hotter ones?
Cool. So the first 3 exoplanets, hot off the presses from TESS, are all in their own individual ways really quite awesome.
Yeah, they are. And you'll notice something about all 3 of them. We know all of them were very, very quick orbits.
Yeah.
So we're not looking for planets that go around every 6 years, every 10 years. And that's the nature of TESS. Because remember that we said that each sector that TESS is looking at, you only get 27 days or so of data.
Yeah.
So it's very difficult. With an exoplanet, you want to see the dip in the light that you get when the exoplanet goes in front of the host star.
The transit.
You want to see that more than once if you're going to work out how long it takes for that planet to go around.
Right. And that's only going to happen if it's orbiting with a period less than 27 days.
Yeah, and in the case, well, we have some stars that have overlaps in terms of the observed. Some of them we will see for about a year, but most of them we're only going to see for 27 days at a time.
Right, so we're really talking things which are within and significantly within the Earth's own orbital period. Within a year, considerably less, ideally.
Yeah, but the wonderful thing is that, again, these are bright stars, so we can follow them up. And actually, in the case of that third planet that we talked about, they were able to go back and find some historic data from another telescope on the ground and look at that and see if they saw the planet as well, which they had, but they weren't sure if it was kind of we're not 100% sure that we're seeing what we think we're seeing, so we'll be cautious about it. But the combined sets of those two data, they were able to put together and really get an interesting story about the star and get a lot of information about it.
So that was obviously a conscious decision when TESS was designed and set up from the very beginning, was we're only going to be really looking for these quite short orbital period exoplanets, missing out on finding new very long period, anything from sort of, Earth's orbit outwards, which in our solar system is Mars, Jupiter, Saturn, Uranus, Neptune. Is there anything at the moment which is still looking for those much larger orbit planets, or is it that just not really on the radar at the moment? What's the situation there?
Yeah, we are looking for those longer things using sort of longer projects, longer ground-based projects. And so doing really long-scale surveys, there's lots of examples. The Sloan Digital Sky Survey, for example, the All Sky surveys will pick up some of those objects. But when we designed TESS, we really wanted to capitalize and get the most out of it that we could, especially looking for planets that might be habitable. And we knew that there were going to be these quite short observation periods. So if you think about if you're going to find a planet that's going on a shorter orbit, if you want to make that planet habitable, then you need to look at cooler stars. So TESS is actually designed to look at the stars that are much, much cooler than the sun. Your Ks, M, dwarfs, so these ones that we mentioned before. It's really tailored to be looking at those types of stars and it's much easier. You don't have to wait around for years and years and years, right?
Yeah, that makes a lot of sense. And also for the other part of TESS's mission, which is looking at variable stars as well, that those are going to be on much shorter timescales than months and years and decades. That's a much shorter time frame. And when you're designing any kind of scientific experiment, then you've got to be choosy. You can't do everything. You can't have the decades long and the minutes, hours, days, weeks and months short mission all in the same thing at once to the right kind of precision. So TESS is inherently a much shorter time frame device.
Yeah, and we learnt so much from Kepler that is being implemented by the TESS mission. So we knew from Kepler that there would be lots of exoplanets going around these cooler stars. And so we have a reasonable idea of how many we're actually expecting to find. So TESS's real goal is to find somewhere on the order of 1,500 exoplanets. Most people would agree, I think, that we're probably going to find more than that. Mm-hmm. We're quite good at finding exoplanets now. And the real goal is to find about 300 that are Earth-sized, maybe 50 that are Earth-sized in the habitable zone. Those are our objectives, if you like.
Okay, all right. Well, we're off to a very good start. And by we, I'm including myself in the astronomical community as ever. Before we finish this episode, though, there's something else, isn't there? Because you have actually been checking out in your own research some of the data that's come down off TESS. You're actually getting your hands dirty as we speak. So what have you been looking at?
Yeah, so of course, TESS's data release that happened in December was really useful for me as well. We had, in our program, we had about 5 stars that we knew were coming down in the first 2 sectors of data. That these are stars that we've been looking at for many, many years, and we're really interested in them. So I'm working my way through those stars at the moment. And
so what makes these stars interesting to you? What are you looking for?
So these are my Gamma Dor stars, and what we're looking...
Your Gamma Dor?
My Gamma Dor stars. They're all mine.
They're mine. They're mine. They'll all be called Emily.
Yeah, so these are types of variable stars that I study. It's kind of a smaller category of variable stars, but with huge interest and huge potential to do some really interesting physics with them. So they're a little bit hotter than the sun, and they pulsate. So they have the surface of the star has pulsations running through it. And these pulsations originate from very, very deep within the stellar interior. And that's so useful because we can't go stick thermometers and probes into stars to see what's going on inside of them. All we ever see is the surface, and all the information we get is from the surface of these stars. And so we have to use things that happen on the surface to work out actually, how big is the core of a star? Is the core rotating inside a star? Is it rotating at the same speed as the surface of the star is rotating? That's a really interesting question.
Yeah, I mean, my natural inclination would be, surely it's got to, but of course it doesn't have to, does it? It could be doing all sorts of interesting stuff, which would be doing some really interesting stirring activity inside the star itself, one would think.
Yeah, exactly. And so I use these stars to work out, to look at the pulsations, work out what the pulsations are doing, and from that we can start to understand what's going on in the very, very deep layers of the star. Very
cool. You showed me a graph, which I'm just looking up on your whiteboard here in your office, of some of the data that you've been looking at already. And when I naively think of the concept of a variable star, I imagine something which is just sort of pulsing, gets brighter, gets dimmer, gets brighter, gets dimmer. But this is much more complex than that. This is not just it goes up, it goes down. It goes up a bit, goes down a bit, and then up again and down. It's really quite low this time, and then up a bit, and it's really quite complex. There's a lot of stuff in here.
Yeah, and this is a wonderful star. So this is a star that I'm working on as part of a huge team. So there's a whole big group of us, and myself and my PhD student were sort of allocated this star. Here, you look at this one.
This one's yours.
Yep, and we'll put all the information that we get from everybody who's individually working together into what we call the first light paper. So this is kind of understanding for the first time what TESS is going to be able to do with all the different types of stars that we're interested in.
So first light being the term for literally the first bit of light that gets into the device. Let's have a look and see what came out of that. So maybe not the first photons specifically, but the first data release is what you're talking about.
That's exactly right. And we can use that to sort of say, well, what can we project that we're going to be able to do over the next few years with the TESS data? So we were looking at the star. It's a really exciting example because it's actually a star that I didn't know was a Gamma Doradus star. In fact, nobody knew it was a Gamma Doradus star.
What's a Gamma Doradus star? What does that mean?
So that's the type of variable that I'm looking at. And what we thought this particular star was, up until Tess looked at it, was we thought it probably was a Cepheid. Now, Cepheid is another type of variable star. It's probably the classic type. It is one that you mentioned before where the surface gets brighter and then dimmer and brighter and dimmer. And usually in a Cepheid, you might have one. If you're very lucky, you'll have two periods that go on. They're very, very classic.
And they're very regular, aren't they?
Very, very regular. Yeah. So the light curves just look like going up, going down, going up, going down. And you just get that repeated. So we thought that this was a Cepheid. Well, in the 60s, when people started first looking at the star, that's what it was kind of classified as. Nobody knew what a Gamma Doradus star was in the 60s. We only knew about them in the 90s. So that was, but they, even in the 60s, they thought, not sure. It's not really behaving like we would think it is. But, there's a lot of stars in the sky, so we didn't really look at it again.
Sure, there's a lot of choice. Yeah.
Until recently. And then when we got this test data, you can instantly see you don't get this very periodic up, down, up, down, up, down, up, down. You sort of get, as you say, going up, down. Oh, it's going down a bit. Oh, no, it's going to go down a bit more. Oh, no, it's going to go up. No, down, down, down.
There's a lot of things competing in this light curve.
Yeah. And what that means is that you don't have just one pulsation going through the star. You've got Lots. And we're still working on exactly how many. We think there's at least tens, maybe even 100 different pulsations going through this star.
And do you know, what kind of dynamics could be causing that? Or is it just that this is a really complicated structure and there's weird stuff going on? Is that what you're trying to find out?
Yeah, exactly. Well, we think that probably most Gamma Doradus stars do have lots of pulsations going through them. How many we're still trying to understand that. But this is effectively going to be a discovery of a brand new Gamma Doradus star. So we're going to take our number of known Gamma Dor stars from maybe kind of 70 to 71, which is, it doesn't sound all that exciting when you say it that way, but for me that's super exciting.
Well, yeah, this one's yours, and we'll call it Emily. Well, that's where we've got to wrap it up for another week of Syzygy. Look, we know we've been quiet for a while, but we're going to get back into the normal rhythm. A bit like a Cepheid variable, we're going to get back into that constant rhythm, or as constant as we can make it anyway. Roughly every week, we'll see how we go. But you can be pretty sure that there's going to be lots of more Syzygy goodness coming your way. Joining me, as ever, on the microphone has been Emily Brunsden. Emily, it's good to be back in 2019.
It's so exciting, and we've got so much new science to talk about. I'm really looking forward to it.
It's going to be a very, very good year. So listen, if you enjoy the show, you really should check us out on the various social medias. Emily, how do people find us on social media?
So,
where are we?
We're everywhere.
We're everywhere.
The universe is big, and so is Syzygy. So you can catch us up on Twitter.
Yes.
In your 160 characters or less.
160? Isn't it 230 now? 240? I don't know. It's a number of characters. And we are at Syzygy Pod on Twitter. You can also check us out on Facebook, facebook.com/syzygypod. Generally, if you're not sure, just search us for Syzygypod. We're probably out there somewhere.
SYZYGY.
That's right.
That'll get you there.
In case you haven't figured that one out yet. Now, coming back into the new year, if you enjoy listening to us and you're thinking to yourself, you know what, I want as much syzygy as humanly possible, there are a couple of ways that you can help us out. First of all, tell as many people as possible. We have a reasonably good sized audience for the show, but we would love it to be bigger. We want to reach as many people around the world who are astronomy mad as we are. So tell your friends, tell your family, leave us a review on iTunes, on Apple Podcasts, on Spotify Podcasts, wherever you can leave us a review. Throw us some stars. Tell the world how much you enjoy the show, because that really helps. It helps us to rise up through the noise of the podcast world. There are a few of them out there, and we want to get to the top. The other way that you can help us is, if you're really, really keen, you can go to patreon.com/syzygypod, and that's where you can become a supporter of the show. You can sign up to throw $1, £1 at us every time we release an episode. You can throw more at us if you really want to. You can throw enough so that we can fly down to South America to see the eclipse in 2022, something like that. And if you become a Patreon of the show, we'll be eternally grateful. That would be a really awesome thing. But if you don't want to go that far, just spread the word. That's all we ask. Look, that's going to have to be all for this week. So catch us again next week, in about a week's time, for another episode of Syzygy. We'll be talking more astronomical nonsense. Until then, Emily, catch you later. Bye. Now, this is episode 28.
28.
It is true.
How did we get to 28? Weren't we like on episode 11 or something?
Yeah, well, that's how it works. It's a little bit like children. Suddenly they grow up. Apparently, I've got a 13-year-old, and I don't know.
Happen?
I don't know. As far as I'm concerned, she's about 3 inches high, and still being bottle fed. So I don't know how that works.